Hello and welcome to Physics Talk. Here we discuss various topics on physics and try to clear all your doubts. So come on, let's begin. Today we discuss about the states of deuteron. Deuteron is the nucleus of deuterium, which is an isotope of hydrogen. It contains one proton and one neutron. It is observed that deuteron has only one energy state, that is its ground state. Since it always exists in its ground state, it is assumed that deuteron possesses the minimum values for its quantum numbers. This means deuteron exists in 1s state, where 1 is the value of principal quantum number and s stands for the orbital angular momentum quantum number 0. Now let us look at the magnetic dipole moment of deuteron. Remember, the magnetic moment of a particle is related to its angular momentum. A charged particle having orbital angular momentum has corresponding magnetic moment due to this orbital motion. Similarly, a charged particle having spin angular momentum has corresponding spin magnetic moment. However, neutron, although it is a electrically neutral particle, it still possesses a spin magnetic moment. Now coming back to deuteron, its total magnetic moment should be the vector sum of magnetic moments due to orbital and spin motion of its constituent particles. As we discussed earlier, since deuteron exists in its ground state only, both proton and neutron are assumed to have the orbital angular momentum quantum number L is equal to 0, which is also called as S state. Since the value of L is 0, there is no corresponding orbital magnetic moment for both of these particles. Therefore, they have magnetic moment due to their spins only. Hence, the magnetic moment of deuteron is the vector sum of the spin magnetic moments of proton and neutron. The magnetic moments of proton and neutron are known. Moments for proton is 2.7925 E h cross divided by twice mp. mp is the mass of proton, and moment of neutron is minus 1.912 E h cross by 2 mp, twice mp. E h cross by twice mp is treated as a unit of magnetic moment called nuclear magneton. Thus, the magnetic dipole moment of deuteron is calculated to be 0.8797 in the unit of nuclear magneton. However, when determined experimentally, this comes out to be 0.8574 magneton. So there is a mismatch of 0.0223. Although the discrepancy is small, it requires explanation. So let us revisit the calculations done. While calculating total magnetic moment, we neglected the contribution from orbital motion by assuming the orbital quantum number L to be 0. Now, the measured value of the magnetic moment indicates that these assumptions may not be exactly correct. On the other hand, taking the next allowed value of L, that is 1, would result in large magnetic moment in comparison to the small mismatch. The calculated value can be tailored to match with the measured value by taking a value of L intermediate between 0 and 1. That is a fractional number, but that is of course not allowed. L can have only discrete numbers. Therefore, the only way out is to have mixed values of L, 0 and some other value. Now we will focus on what could be that some other value. Here we invoke one principle. States of even parity and odd parity do not mix together. We know that the value of L determines the parity of a state. When L is even, parity is even. When L is odd, parity is odd. L is equal to 0 signifies even parity state. L is equal to 1 signifies odd parity state. Again, L is equal to 2 signifies even parity state. As per the principle stated before, the mixture of L is equal to 0 and L is equal to 1 is not allowed. Mixing of L is equal to 0 with L is equal to 2 is allowed. These two states are also called S state and D state. In this way, it is found that Deuteron has both S and D states. The Deuteron wave function psi d can be expressed mathematically as a combination of one S and one D states. The coefficients a0 and a1 determines the weightage of these two states. It is found that if a0 square is said to be 0.96 and mod a1 square is to 0.04, the calculated magnetic moment tallies with the observed value. This physically means Deuteron spends 96% of its time in S state and 4% of its time in D state. One important point to note here is that it does not remain in these two states simultaneously. It continuously fluctuates between S state and D state. Say at some point of time it is in S state. Then it jumps over to D state, remain there for a very short period of time and then come back again to S state. In this way, the process continues. In this way, by analyzing the magnetic dipole moment of deuteron, we have learned that it largely remains in 1s state. Although intermittently it goes to 1d state, remains there for a very short period of time and then comes back again to the 1s state. This finding about the states of deuteron gets additional support from the analysis of its quadrupole moment. Electric quadrupole is formed by a couple of electric dipoles and its strength is quantified by its moment. In case of atomic nuclei, there are no negative charges present, only positively charged particles are present there. However, a collection of like charges, either positive or negative, can also have quadrupole moment. For example, take an assembly of positive charges. If the charges are distributed such a way that they are spherically symmetric, then the assembly will not have any quadrupole moment. Any departure from its shape from the spherical symmetry will result in the formation of a quadrupole and will have its quadrupole moment. It behaves as if the extra bulge from the spherical symmetry has extra positive charges and the portion intruded inside the spherical symmetry has negative charges. The important point to note here is that as long as the charge assembly have spherical symmetry, it would have zero quadrupole moment. It is found experimentally that deuteron has a quadrupole moment, although the value is very small. This non-zero value of moment clearly indicates departure from the spherical symmetry, which in turn tells that deuteron is not in pure L is equal to 0 or S state, because we know S orbital is spherically symmetric. Again, since the moment is very small, it indicates very little departure from the spherical symmetry. It supports our conclusion drawn from the discussion over the magnetic moment of deuteron that there is only 4% departure from the spherical symmetry. In this way, from the treatment of magnetic moment and electric quadrupole moment, we have learned about the S and D states of deuteron. We have also found out that our initial assumption L is equal to 0, although not correct exactly, it is not fully wrong either. And now I would like to draw your attention to something that I saved for the last part. As we have found out and also stated that the angular momentum of deuteron goes on changing continuously from SD to SD again. This is against the established norm. The angular momentum of a closed system cannot just change by itself. There must be a torque acting on it. The way some force must be applied to change the linear momentum, a torque must be in action to alter the angular momentum. Hence, there must be a torque acting in the system, and let us investigate its origin. A torque is defined as the angular gradient of potential with a negative sign. This implies potential present in the system has an angular dependence. In other words, potential of the system is a function of the angle theta. When this happens, the force in play is called a non-central force. In contrast, for central forces, potential is a function of position vector r only. In order to explain it more clearly, let us look at this diagram of deuteron. We take the simplest approximation that the two nucleons are orbiting around their center of mass in circular orbit. Two diagrams show different positioning of the nucleons. If the force of interaction acting between the particles is a central one, then in both the cases they will experience same amount of force or potential because the distance between them remains same. But in case of a non-central force, they will experience different amount of force and potential because of different angular orientation. Now the angle has to be measured with respect to some reference direction. Inside an atom or nucleus, the only direction can be specified is the direction of spin. In the first diagram, the line joining two nucleons is perpendicular to the spin direction, whereas in second diagram they are parallel. And in case of a non-central force, The potential is different in these two cases because of this angular difference. Since a torque must be acting in the system, the potential is different in different angular orientation, and this shows nuclear force has a non-central component. And thus the fact that deuteron exists in both S and D states leads us to a very important finding about the nature of nuclear force.